Just as water current is the flow of water molecules, electric current is simply the flow of electric charge. If we have a conducting wire like this, we can calculate the magnitude of electric current by counting the number of charges passing through it over a period of time. But what causes charges to flow from one end of the wire to the other? Say we have two conducting plates A and B, one having a net negative charge while the other the opposite. If we are to place a connecting wire between them, free electrons present in the wire will naturally flow from left to right. Some of the excess electrons from plate A will even move to plate B, resulting to plate A becoming less negative and plate B less positive. The migration of electrons will continue until the overall charge of the two plates have become equal. We can liken what happened here to how water flows from a place of high pressure to a place of low pressure. More water is present on the left tank than on the right tank. More water means larger weight is pressing on the water molecules at the bottom of the tank. The pressure pushes this water molecule through a pipe connected to the right tank, where there is lower pressure. The water will only stop flowing if the water level between the two tanks have become equal, or there is no more difference in pressure. In our previous setup, we will call the difference in pressure as difference in potential or potential difference. The negative charges are repelled by plate A, the plate with high potential, causing them to move to plate B, the plate with low potential. Once enough negative charges have neutralized enough positive charges, the two plates acquire the same electric potential, and no more flow between the plates happen. In short, without potential difference or voltage, which is another term for it, there will be no flow of charges. Current will not exist. We can add to this setup another conducting wire that connects the two plates together. But electrons will not return to the negative plate. This is because charges naturally flow from a point of high potential to a point of low potential, as in from plate A to plate B. To do the reverse is to expend energy. Just as a large stone will roll down a hill on its own, but it cannot climb a hill by itself. A person needs to push it up. This setup is actually a representation of a simple circuit. A simple circuit is a closed conducting loop composed of connecting wires, an electrical load, a battery, and a resistor, which we will add to the circuit later on. A battery has two terminals, the positive and the negative one. In this circuit, the negative terminal is the place of high potential. So naturally, electrons will flow from this terminal to the positive terminal on its own. The battery therefore is the source of voltage or potential difference. If we say that our battery has a voltage rating of 12 volts, that means that every unit of charge will receive 12 joules of electric energy, energy that can be expended to power electric load like our light bulb here. If all electric energy is transformed to light, the charges loses its 12 joules of energy after passing through the filament of the bulb on its way to the positive terminal. To keep the light bulb on, a continuous supply of charges is needed. Hence, the battery needs to maintain the potential difference of 12 volts between its terminal for charges to keep flowing. To do this, chemical reaction happen inside the battery. Two electrodes composed of zinc anode and a manganese cathode performs an oxidation reduction process. To keep it simple, the zinc anode oxidizes and produces negative electrons which keep the negative terminal negatively charged. Meanwhile, the manganese cathodes consume electrons from the positive terminal during reduction process, keeping the terminal positive. Of course, this cannot happen forever, and when the battery can no longer maintain the voltage across its terminal, we say that it has been discharged. The oxidation process inside the battery releases energy, which the electrical charges carry to the light bulb to keep it on. In this way, the cycle of flowing charges from one terminal to the other continuous. It is worthy of noting that electric devices such as light bulb has a power rating, which means that there is a specific amount of current it can allow to pass through it for it to operate at its best. If there is too low of a current, the light bulb will be dim, but too much current can cause the bulb to heat up or even blow up. To avoid this, resistors are added to the circuit. You can think of resistors as water valve, which regulates how much water current can pass through a garden hose, for example. Light bulbs placed in circuits without resistors might appear brighter for now, but they would have a shorter lifespan. Voltage, current, and resistance are important elements of a circuit. They can be related to one another using the Ohm's law, a fundamental equation when studying electricity. The Ohm's law states that current is equal to the voltage divided by the resistance of the circuit. This means that if voltage increased, the current through the wire will also increase. But if resistance is increased, the current will instead decrease. Adding more light bulb in series will add up the resistance, so they will look dimmer, which indicate lesser current flowing through. But putting the two light bulbs in parallel will reduce the overall resistance, as there are more pathways for charges to flow. The light bulbs will then look brighter. As a final note, remember that a simple circuit still operates on conservation of energy. The chemical energy stored in the battery transforms into electric potential energy, which can be further converted to other useful forms. Mechanical if a fan is connected to the circuit, light if you instead have a bulb, or heat if you have a flat iron, among others. The rate at which electric energy is converted into other forms is calculated as electric power. Power can be computed by multiplying the total current to the voltage across the circuit.